Okay. Um, Today, what we'll do is we'll start talking a little bit more about the idea of chemical reactions and gases. Earlier this week, we looked at the gas laws. So now what we're going to do is we're going to apply the gas law, the ideal gas law, to a chemical reaction. Okay. So when we think about a chemical reaction, we generally have, not always, but generally we have two or more reactants. So we might have reactant 1 and reactant 2. And then what we do is we mix those together, and then we get our products, which could be product 1 and product 2. Now, typically, when we deal with that, the types of problems we've looked at thus far, there are two ways in which we dealt with the amounts of the reactants and the amounts of products. The first one was we're given the mass of the first reactant and given the mass of the second reactant. And then we're asked to find the mass of the first product and maybe the mass of the second product. So that's one way in which we can figure out the amounts of materials. The second way was we might be given the molarity of the first one and the volume of the first one. And likewise, we might find the molarity and the volume of the second one. Oops, 2. And then from that, we can figure out the molarity of the first product. I'll call that P1. And we might be able to find the molarity of the second product. Okay. That's typically done in titration problems. So for example, if you take acetic acid, which is the active ingredient in vinegar, and mix it with sodium hydroxide, a strong base, you'll get a reaction that takes place, and you can figure out what the concentration of the acid is in the vinegar. But what we're going to look at today is a third method, which is where we use the ideal gas law. And again, this is only valid for gases. Technically speaking, it's only valid for ideal gases. But PV equals nRT, this ideal gas law, we can use that to figure out amounts of materials. Okay. So again, the P stands for pressure, the V is volume, N is the number of moles, R is the universal gas constant, and then T is the temperature. So let's take a look at an example of how this works. I'm going to pull up a problem here. Let's move this right over here. Okay. So imagine that we do the following. We have mercury 2 oxide decomposes into oxygen gas and mercury metal. Okay, and then I'm going to give you some numbers. Suppose 40.0 ml of oxygen is produced at 120.0 degrees C at exactly 1 atm. Okay. Calculate the mass of mercury oxide. Calculate the mass of mercury oxide that decomposed. Okay, there's an interesting example. Okay. So it's called mercury 2 oxide. So mercury 2 oxide means that the charge of the mercury is +2. Oxide has a charge of -2. So that means the formula for mercury 2 oxide is just HgO. Each atom has the same magnitude of charge. It's a solid. And going back to chapter 3, decomposition is where something, typically a compound, breaks up into smaller components, usually, often, not always, but often elements. So for this one, it's producing oxygen gas. Remember, oxygen's diatomic. And mercury, metallic mercury. Now, mercury is a unique element for us in that it's the only metal that is a liquid at room temperature. All the other metals are solids at room temperature. Gallium is a metal that melts a little bit above room temperature, so if you put it in your hand, it'll melt. But mercury is the only one that is actually a liquid at room temperature. Okay. In fact, there are very few elements that are liquids at room temperature. Bromine, Br2, is a liquid at room temperature, as is mercury. Okay, so notice I wrote the equation. It's not balanced though, so let's balance it. We have 1 mercury on both sides, so that's good. But we have 2 oxygens on the right side, the product side, and only 1 on the left, the reactant side. So let's put a 2 in front of the HgO. So that gives us 2 oxygens, but it also gives us 2 mercuries. So let's put a 2 over there. Okay. Now, the reason we need the balanced equation is because they're asking us about amounts. Whenever they ask us about amounts of something, we generally need the balanced equation. So let's take a look at the numbers they gave us. They say that 40 milliliters of oxygen is produced. So I'm going to write down below the O2 40 milliliters, 40.0 milliliters, right? Notice the units, milliliters. That tells us it's a volume. So we have a volume problem here. It also tells us earlier in the problem that oxygen is a gas. So we know it's a gas, 40 milliliters of gas. We're also told that this occurs at a temperature of 120.0 degrees C and a pressure at exactly 1 atm. Okay, so really what it looks like what we have here is a problem where we have the volume of a gas and we know its temperature and we know its pressure. PV equals nRT. We've got 3 of those variables there. So what I'm going to note is that for oxygen gas, PV equals nRT should work, right? We have information that is, corresponds to that ideal gas law. The one that we don't know is the number of moles N, right? That's the one we don't know. We do know P, we do know V, we know R, and we know T, but we don't know R, we don't know N. So let's read the question again. Calculate the mass of mercury oxide. That's this right here. There's your mercury oxide that decomposed. So this is a very standard stoichiometry problem. Amounts of reactants, amounts of products. How are they related? The way we dealt with that in chapter 3 was by using what's called the molar ratios. We would say that there are 2 moles of mercury oxide decomposed to give you 1 mole of O2, right? We're just using the coefficients to figure out those relationships. So here's going to be the strategy. Step 1, find the moles of O2 from PV equals nRT. Remember, the ideal gas law is only valid for gases. It's not valid for solids or liquids. So we can't use PV equals nRT to do anything with HgO. We can only do it for the gases in the problem, so that would be O2. Step 2, find the moles of HgO, mercury oxide, from the moles of O2, okay? And for that one, you're going to use 2 moles HgO equals 1 mole O2. And then the question is find the mass. We want to know what the mass of HGO is, right? So step 3, we find the mass of HGO from its molar mass, right? If you know the number of moles of a substance and you know its chemical formula, you can use the molar mass to find the number of moles. Okay, that's back what we learned in chapter 3. So there we go, 3 steps. It looks like it should work out okay. So let me do some of the calculations up here. Okay. P equals nRT. So the gas law, P equals nRT. We want to find the number of moles of O2. So I'm going to divide both sides by RT. So N is equal to PV over RT. So the pressure is 1 atm. That's an exact value. That means when they say it's exact, that means you don't have to worry about the number of sig figs for that value. Just ignore it. The volume is 40 milliliters. But remember, the gas constant R is typically in liters. So I'm just going to take the 40 milliliters and divide it by 1,000. And that'll give us 0.0400 liters. Just convert that into liters. Gas constant, 0.082057 atmosphere liters per mole K. And then the temperature, remember again, with gas laws, you have to have the temperature in Kelvin. So I'm going to take our 120 and add 273.15, and you get 393.15 Kelvin. So 393.15 Kelvin. Okay. A lot of units in there because the R constant has 4 units in it. So remember, you're going to do all this dimensional analysis, but it should work out to be moles, right? If we're trying to calculate N, the units should be in moles. Okay, so 0.04 times 1 divided by 0.082057 divided by 393.15, and you get a very small number. It's 1.240 times 10 to the minus 3 moles of O2. Okay, remember it's O2 because we're using the gas law. If you're using the gas law, it's going to be the moles of the gas. Now our second step is we use the balanced equation. The relationship is 2 moles of HGO react every time you get 1 mole of O2. So I'm going to take our 1.240 times 10 to the minus 3 moles. This is O2, and then it's 2 moles of HGO for every 1 mole of O2. So that's just going to double that value. So you get 6.20 times 10 to the minus 4 moles, but now this is HGO. Okay, so we're almost there. We've got the number of moles of HGO. The last step is just to figure out how much this HGO weighs. Now, mercury is 200.6 grams per mole. Oxygen is 16 grams per mole. So if you add them together, you get 200.6 plus 16. So you get 216.6. So that's the number we can use there. So our last step, step 3, 6.20 times 10 to the minus 4 moles of HGO. And it's 216. It's very heavy because mercury is a heavy metal. Okay. Use the molar mass, get rid of the moles, and then that'll give you a value. So times 216.6. And wow, it's still kind of small. 0.13428 grams of HGO. Still a lot less than a gram. Now let's go back over the sig figs. It looks like we had 3 here. It told us this was exact, so we'll ignore the 1 atm. Temperature's in 4, but it looks like it's 3. It looks like 3 is our limit. So that means it's going to be 0.134, right? The number after the 4 is less than 5, so 0.134 grams of HGO. Okay. So let's just kind of review what we did there, a couple details, but essentially what you do is you look at the problem, and if they give you a gas and they're asking you to figure out the amount of the gas, the amount of another material in the reaction, you need the balanced equation for that. The relationship between one substance and another is the balanced equation. Then you take a look and see what you're given. You're given the volume of a gas, you're given its temperature, and you're given its pressure. Well, that's enough to use the ideal gas law. So what you do is you take those variables, PVT, and you use those to find the moles. So PV equals nRT, that'll give you the moles. Then you say, okay, well, they don't want to know how much O2 is in there. They want to know how much HGO broke up, decomposed to form the O2. So you're trying to find another material. That's where step 2 comes in. You find the moles of another material by using the balanced equation. Okay. And then once you've got that amount of material, if you know the formula, you can use the molar mass of that substance in order to figure out the number of grams. So if they just said, what's the number of moles of HGO, you would stop at that second step, which is right here. Typically, they're going to ask you for the, if it's a solid, they're going to ask you for the number of grams. They're going to want the mass. If it's a liquid, typically they'll want the mass as well. Okay. Any questions on that particular stoichiometry problem? Okay, let's see. Let's try one more. I'll show you a second one here. Okay, so in this particular problem, they're talking about concrete, and concrete uses calcium carbonate. So we'll start by writing the balanced equation for the decomposition of calcium carbonate which is CaCO3, that's a 3, into calcium oxide and carbon dioxide. Okay, so that's our first step. And then we're also going to do a calculation. So the calculation would be, suppose 32 liters, 32.0 liters of CO2 carbon dioxide gas are produced in the reaction. At 200.0 degrees C and 1.05 atm. Calculate the mass of CaCO3, the calcium carbonate that reacted. Okay. very similar to the previous one, really just a different equation, but the same type of calculation. So let's take a look at this one. We want to write the balanced equation for the decomposition of calcium carbonate into calcium oxide and carbon dioxide gas. So notice that that's the gas there. So Ca, CO3 is breaking up into CaO and CO2. And that one's a gas there, okay? Again, if it's a gas, you can typically use the ideal gas law. So let's see what information they get. Well, first of all, let's see if it's balanced. There's one calcium on both sides. There's one carbon on both sides. And it looks like there's 3 oxygens on both sides, right? There's 3 in the calcium carbonate, and then there's 1 oxygen in calcium oxide and 1 in the carbon dioxide. The CaO is called quicklime. And so it looks pretty good. Looks like it's already balanced. No need to do any extra steps to balance this equation. So that's good. So it tells us that the carbon dioxide gas, so that's right here, has a volume, right? Liters is volume, so that's 32 liters. So we know the volume of the CO2 is 32.0 liters. They also tell us the temperature of that gas, 200 degrees C. So remember, if you add 273.15, you get the Kelvin. So that's 473.15 Kelvin. So this is happening at a very high temperature, 200 degrees C. That's pretty hot. What is that? That's about 400 degrees Fahrenheit. So that's the temperature you might put something in an oven. It's pretty hot. And then you've got the pressure. In this particular problem, it's not exactly an atmosphere. It just says it's 1.05 atm. And there we go. So it looks like we've got enough information there for a gas to find the moles of that particular material. We've got an equation that's balanced. So if we have the number of moles of CO2, we can find the moles of this material too, right? Moles, that's the relationship between moles between different materials is the balanced equation. It'd be sort of like an analogy would be, if I counted the number of cars on the road, I would also implicitly know the number of wheels on the road, right? If there are 10 cars on the road, you know there's 40 wheels because each car has 4 wheels. So same thing with this one. If you know the number of moles of CO2 that were produced, you also know the number of moles of calcium carbonate that reacted, decomposed, okay? So it looks pretty good. And then it tells us to calculate the mass of CaCO3, calcium carbonate. So you can find that because we can definitely calculate the molar mass of CaCO3, okay? So let's do the first step. Let's deal with the oxygen first. PV equals nRT. By the way, there are more complicated gas laws out there. We just use the ideal gas law in this course, but there's ones that are much more complicated for real situations. So first step is we want to find the number of moles of O2. So divide both sides by RT. So you get the number of moles of O2 is PV over RT. Remember, this is only good for gases, so it's only going to be good for the O2. You can't use PV equals nRT for CaCO3 because it's not a gas. Okay. So in this particular case, the pressure is 1.05 atm. The volume is in liters already, so we don't need to divide that by 1,000. So 32 liters. And again, it needs to be in liters only because the R value is in liters. So 0.082057. I'm going to have a little more room in here to show you how the units work out. And then our temperature is 473. Notice that with this particular problem, I converted the temperature immediately. That's not a bad idea to deal with gas law problems because you need to have it in Kelvin. So atmospheres are gone, they divide out. Liters are gone, they divide out. Kelvin are gone, they divide out. And you're left with 1 divided by 1 over moles. So this would be moles of O2. Okay. So 1.05 times 32.0 divided by 0.082057 divided by 473.15. And you get, this is a little bit larger than the one last time. This one now is 0.8654. And it looks like we're going to be limited by 3 significant digits, right? There's 3, there's 3. So our answer is going to get rounded to 3. So I'm going to keep 1 extra through these calculations, and then at the end, I'll round it to 3. So step 2, moles of CaCO3. And the relationship is, it's 1 to 1, right? Every time 1 CO2 is produced, 1 CaCO3. So what you do is you say 0.8654 moles of O2. I put O2, I'm sorry, it's CO2. CO2, okay. Moles of CO2 times 1 mole of CaCO3 divided by 1 mole CO2. Okay, well, it's just gonna, it's a trivial answer. You're gonna get 0.8654 moles of CaCO3. Okay. Step 3, we want to find the mass. Remember, grams of CaCO3. Okay. Well, let's figure that out. The molar mass of calcium is 40.08. Carbon is 12.01. And then oxygen, there's 3 of them. 16, 3 times 16. So 40.08 plus 12.01 plus 48 is 100.09. 100.09 grams per mole. That's your molar mass of CaCO3. Okay, so now we have the moles of CaCO3, 0.8654. And then it's 100.09 grams per mole. Okay, so times 0.8654. Looks like you get 86.62. But it looks like we're limited to 3 sig figs. So I'm going to round this to 86.6. And there you go. Okay. So it's interesting. These problems are interesting because what's happening is you're going to have completely different units for different materials. If it's a gas, you're typically not going to see a problem where they give you the mass of the gas. You could do gas problems with masses. The problem is it's hard to measure the mass of a gas. It's not impossible. It takes a little more effort to do that. But measuring the pressure of a gas is very easy. Measuring the volume of a gas is very easy, and measuring the temperature of a gas is very easy. So typically gases are given in amounts of PVT, whereas solids are generally weighed out on a balance. Okay, so this problem connects those 2 different states of matter, PVT for gas, mass and moles for a solid. Okay. Any questions on the second example? Very similar to the first one, pretty much the same kind of problem. Okay, all righty. Okay, so let's take a look then at gas mixtures. So this is section 10.5, gas mixtures. So I'm going to introduce a couple of new terms. One is called the mole fraction. And I'm going to use a symbol of a capital X for mole fraction. And then the second term I'm going to introduce is what's called the partial pressure. P sub A. Okay. So really what we're dealing with here now is the issue of mixing gases together. What happens when we mix gases together? So for example, inside of a balloon, you have air, right? And air is approximately, by volume, it's approximately 78% N2, nitrogen, and about 21% oxygen, O2, and about 1% CO2, AR, KR, H2O, and some other gases as well. Okay, so it's a mixture of gases. And so under many circumstances, we're interested in doing calculations when we don't just have one gas in the container, but we have more than one gas. We have a mixture of gases. So we're going to deal with this in the following way. What we're going to do is we're going to define this mole fraction as, so I'm going to call this mole fraction of gas 1. And based on the name, mole fraction, you can kind of figure out what it is. It's a fraction, so it's a ratio, something divided by something, right? Somehow it has to do with moles. So we're going to call it the mole fraction of gas 1 is the moles of gas 1. Okay, however many moles of whatever gas you're talking about, it could be oxygen, it could be nitrogen, over the moles of gas 1 plus the moles of gas 2 plus the moles of gas 3 plus the moles of however many gases you have. If you have 20 gases in there, it would be the moles of all 20 gases. So let's make that a little bit simpler. I'm just going to write this as moles of gas 1 over the total number of moles of all gases. Okay, so in this balloon, you have oxygen, you have nitrogen, you have carbon dioxide, argon, krypton, all these other gases. The mole fraction is calculated for each gas. So for air, the mole fraction of oxygen would be the moles of O2 over the moles of N2 plus the moles of O2. Remember, because O2 is part of it, plus the moles of CO2, plus the moles of all the gases that are in there. And typically we want to use symbols for this. So I'll write it this way. NO2, N using the symbol N for moles, over N total. And that would be a formula that you could use to calculate the mole fraction of O2. Okay. Now, it's unitless. It doesn't have any units, and typically we don't do it as a percentage. It's not that useful to do it as a percentage. You could do mole fraction percentage or mole percentage, I guess. You'd multiply it by 100, but typically it's just the moles of the gas you're interested in divided by the total number of moles. Okay. So let's take a look at an example. Suppose we have, I'm going to actually go ahead and create a new whiteboard. Suppose we have a 7-liter tank at 4.6 degrees C is filled with 9.41 grams of boron trifluoride gas and 9.99 grams of chlorine gas. I'm sorry, chlorine pentafluoride gas. Okay. Calculate the mole fraction of each gas in the mixture. Okay. All right, so we have two gases. We have 9.41 grams of boron, that's B, right? Tri means 3, fluoride, so F3. So we have 9.41 grams of BF3, that's a gas. And 9.99 grams of chlorine pentafluoride gas. So 9.91 grams of chlorine. Penta's 5, so pentafluoride. Calculate the mole fraction. Now, just a little tip, if you see a problem and they ask you to calculate the mole fraction, typically you don't have to worry about any kind of chemical reaction. You just have to do the mole fraction calculation. So you're not likely to see a problem where you have to then balance the equation and figure out the number of moles of one of them from the other. Typically, the mole fraction is just a static problem. You just calculate the mole fraction separately. Okay. Also notice for this problem, they give some information that's what's called extraneous information, meaning you don't need it for this calculation. We don't need the volume of the tank. We don't need the temperature of the tank either. If they gave us the volume and the temperature and the pressure, that would be enough to calculate the number of moles. So we could use PV equals nRT. But they actually gave us the mass of each material. And remember, going back to chapter 3, if you know the mass of a substance and you know its chemical formula, you can calculate the number of moles immediately just by using the molar mass. So no need for that information about the volume or the temperature. Furthermore, there's not enough, they don't give you the pressure. So if you don't know the pressure, you can't find the number of moles of the gas. You need 3 of the variables to find the 4th. So we'll just use the mass. So here's our strategy. We want to find the mole fraction of each gas. So I'm going to write out the mathematical formula. We want to find the mole fraction of boron trifluoride. Okay, so there's the symbol we're going to use. X for mole fraction, BF3 to tell us the mole fraction, so we know which one goes on top. So this would be the moles, N, of BF3 divided by the total number of moles. So remember, there's only 2 gases here. This is gas 1, this is gas 2. So I'm just going to write it as moles of BF3 plus moles of chlorine pentafluoride, right? That's the total number of moles on the bottom. So if we could just put the moles in, we'd have an answer. Now here's a common mistake. I'm going to write here, don't do this. It's typical for people who haven't done a lot of these problems to then just write 9.41 grams over 9.41 grams plus 9.91 grams. You can't do that because we need the number of moles of each substance, not the number of grams, right? So don't do that. We need the moles of each. So let's figure out what the number of moles are. The moles of BF3, we have 9.41 grams. 1 mole weighs how much? Well, boron weighs 10.81 grams. That's how much boron weighs. And fluorine weighs 19.00 grams. Okay, so that's your molar mass of BF3. Okay, so your grams are going to cancel, and then you just have moles there. Okay, so 9.41 divided by 10.81 plus 3 times 19.00, and it looks like it's 0.138, oops, sorry, 13877. I'll just write 77. Okay. So notice for that one, I'm keeping a couple of extra sig figs. If you keep one extra sig fig, that would be fine. The measurements are 3. So if you keep 4 or more, you're fine. And then we'll round at the end. Let's find the moles of chlorine pentafluoride. That's probably a pretty nasty compound. Anytime you get chlorine and fluorine together, it's not very nice. 9.91 grams. Okay. Times 1 mole, and then it's chlorine pentafluoride. So it's chlorine is 35.45, and then fluorine is 19. Okay, so chlorine pentafluoride. So divide by the molar mass. So 9.91 divided by 35.45 plus 5 times 19, and you get 0.07597 moles of chlorine pentafluoride. Okay, so again, we don't need the temperature or the volume to do this. We just use the molar masses to find the number of moles. Now we can do our mole fractions. The mole fraction of boron trifluoride would be the moles of boron trifluoride. So that's right here. I'll put the units in there, but remember the mole fraction is going to be unitless because the moles are going to cancel. And then divided by the total number. So that would be 0.13877 plus 0.07597. Okay, well, just for myself, I'm going to add those two in the denominator. 0.13877 plus 0.07597. So it looks like you get 0.13877 over I guess that's about right, 21474. So it looks like it's going to be about 2/3, right? 14 over 21 is 2/3, which is 0.6666, 0.67. So it's pretty close to 14 over 21. So let's see, 0.13877 divided by 0.21474. Yeah, it's about 0.646. I'm going to round it to 3 sig figs here. And there's your mole fraction of BF3. Okay. Now, what is the interpretation of that? What that's telling us is that out of the total number of moles, 0.646 out of 1, if you had 1, out of 1, it's 0.646 BF3. That means the rest of it is ClF3. If you wanted to put it in a percentage, you'd say that it's about 65%, 64.6% BF3. The rest of it would be the chlorine pentafluoride. So now let's calculate the mole fraction of chlorine pentafluoride. There's a couple different ways you can do this. The more involved way would be to take the moles of chlorine pentafluoride and divide that by the total number of moles, which we already did, by the way. That's down here. That's the total there. And just take that ratio, okay? So 0.07597 over 0.21474, and you get 3538. Well, let's round it. 0.354. Again, unitless, right? Mole fractions don't have units because it's moles divided by moles. Now, you could do it that way, or you could say, wait a minute, there's only 2 gases in there. So if 64.6% of it is BF3, the rest of it has to be the chlorine pentafluoride. So you could say this: the mole fraction of BF3 plus the mole fraction of ClF5, that's got to add up to 1. If you add those two numbers together, you get 1. Okay? So that means what you could do is you could say the mole fraction of chlorine pentafluoride is just 1 minus the mole fraction of BF3. So that would be 1 minus 0.646. And you get the same answer. Right? Okay, so you can use that method as well. Either one will work. If you have 3 gases, though, you would need to know 2 of them to find the third using that methodology. But if you just have 2, you just take 1 minus that 1 and you'll have it right there. Okay, so those are mole fractions. Now, we can do mole fractions calculations even if they're not gases, but typically, not always, but typically mole fraction calculations are done with gases, and we'll see why that's the case in a moment. Okay. Any questions about mole fraction? Okay. So now I want to show you why we use the mole fraction, and it has to do with this issue of what's called partial pressures. So what we want to be able to do is we want to be able to look at a mixture. So this is a gas mixture. So we have more than one gas. So let's say we have O2 in there, and we have N2 and CO2. What we want to do is we want to be able to find out what the individual pressures are of those gases. And those individual pressures, these are called partial pressures. Partial because they're part of the total. So a typical type of question would be, given the total pressure, because if we're measuring this container, we can put a little probe in there, a little sensor, and we can measure gas pressure. We can do that. It's a pressure probe. There are many different types that are used out there. But it can only measure the total pressure. It can't measure the pressure of each one. They don't work that way. It'd be nice if they did. It'd be amazing if you could develop a sensor that could tell you the pressure of each gas individually. That would be hard to do. Maybe not impossible, but difficult to do. So more typically, we would have a probe that would measure the total pressure, and then we need to have some method to figure out what the individual pressure. If you've ever watched any of these like science fiction movies or shows where they go to an alien planet and then they have to say, hey, what's the deal with the atmosphere? Can we breathe this atmosphere? You need some way to figure out, 1, the total pressure, 2, which gases are in the atmosphere, and then 3, how much of each gas is in the atmosphere. So for example, you might have an atmospheric pressure of 1 atm, but there's no oxygen in it, so you can't breathe it. Or you might have a total pressure of 1 atmosphere and 21% of it is oxygen. That sounds good, but maybe 1% of it is a poisonous gas. Then you still couldn't breathe it, right? So that's essentially what this is getting at, which is how much of each gas do you have in the container, okay? So that terminology we use for the pressure of each gas is called the partial pressure, okay? So what we want to do then is we want to be able to take a look at a problem where we find the partial pressure of each gas. So what I'm going to do is I'm going to show you what the relationship is. There's a couple. The first one is the total pressure, if you have a mixture of gases, is equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas. And it goes on to as many gases as you have. So if you have n gases, like 16, you would just add up the individual pressures. Each of those pressures is called a partial pressure. So P1 would be called the partial pressure of gas 1. P2 would be called the partial pressure of gas 2. So forth and so on. Okay. Now, here's the other relationship that will be helpful for us. The partial pressure of a gas, I'll call it P1, is equal to the mole fraction of gas 1 times the total pressure. And that's very useful for us. Very simple, because we know how to calculate mole fractions. So if we know, so typically this is given, and then we can calculate this, that allows us to calculate this one. Right? We've learned how to calculate the mole fraction. So that's typically how it works. You're given the total pressure, you figure out what the mole fraction is, and then you find the partial pressure of the gas from those numbers. So let me show you an example. The example here is that we have given 2.80 grams of sulfur hexafluoride. This is a famous molecule now, SF6, and 9.42 grams of dinitrogen. Dinitrogen monoxide. Gases are mixed into a tank with a volume of 6 liters, 6.00 liters at 16 degrees C. Calculate the partial pressures of each gas. Okay. So let's take a look at how we go about this. The first step would be to say, if we want to find the partial pressure of each one, I'm going to write it this way. The total pressure is the pressure of the first gas, SF6, plus the pressure of the second gas, pressure of N2O, right? But we don't know either of those pressures, right? So here's what we're going to do. We know the masses of each one. Okay, we have the masses of each one of them. So what I'm going to do is I'm going to find the moles of each. We have 2.80 grams for SF6 and 1 mole. Let me do the calculation here. SF6 is 32.07 for sulfur and 6 times 19.00. So that's 146.07 grams. So for SF6, the number of moles, do a reciprocal here, is 0.01917. Now let's do the second gas, moles of N2O. We have 9.42 grams And 1 mole of N2O is 2 nitrogen, so 2 times 14.01 plus 1 oxygen, which is 16, 44.02 grams. So 9.42 over 44.02, and it looks like you get 0.2140. Okay, so we have the moles of each one. So let's do the following. Let's do the mole fractions. The mole fraction of SF6 is 0.01917 divided by, let's do the total number of moles. The total would be 0.01917 plus 0.2140. So that's 0.2332. So there's your mole fraction there. So 0.01917 divided by 0.2332. So that's 0.0822. That's your mole fraction of SF6. Now let's do the mole fraction of N2O. I'm just going to do 1 minus 0.0822. That's easier, right? And it looks like it's 0.9178. So now you got your mole fractions. So if you take a look at the original equation that I have over here, if you somehow had the total pressure, you would be able to find the partial pressure of each one very easily because we know the mole fractions. So how do we deal with this? What I'm going to do, let me just erase some of this over here so we get some room, is I'm going to find the total pressure using the ideal gas law. And here's how I'm going to do it. The total pressure is going to be the moles of all the gases times RT over V. I'm just using the ideal gas law. PV equals nRT. So if I want to know what the total pressure is, I just take the moles of the gas times RT over V. However, I could also do this. The pressure of each gas is the moles of that individual gas times RT over V. That works too. I can actually use that method. So let me try this. Let's try this with each one. I'm going to do the partial pressure of SF6. That would be the moles of SF6 times RT over V. Now in this problem, let's see what we got. We have V, there's your V, there's your T. So we know that, we know that. R is a constant, we know that. And we have the moles of SF6, it's right there. So for this one, we actually don't even need to use the mole fractions for it. All we need to do is find the moles of each gas and then plug that into our PV equals nRT. So let me do it for SF6. The moles of SF6 are right here. R is 0.082057. And then T, be careful with T. This is in Celsius, so I'm going to add 273.15. So that would be 289.15. So there's your nRT. Divide that by the volume. It's in liters, so you're good there. And so nRT over V will give you the pressure of the SF6. So 0.01917 times 0.082057 times 289.15 over 6.00. And it looks like our pressure of SF6 is 0.0758. Atmospheres would be the units. I'm going to leave in 3 sig figs because it looks like our numbers are 3 sig figs, right? So 1, 2, 3 sig figs. Now let's do the N2O. We need the moles of N2O times RT over V. So the moles of N2O were right here, 0.214. N times R times T. They're in the same container, so they're going to have the same temperature. The temperature was 289.15. And then we're going to divide that by the volume. The volume is the same volume because they're in the same container. Okay. So nRT over V, 0.2140 times 0.082057 times 289.15 divided by 6.00, and you're left with a pressure for N2O. Again, this is called partial pressure. I'm going to round it to 3 sig figs, 846 ATM. Okay. So mole fraction, we have those values here, 0.0822, 0.9178. And now we have what are called the partial pressures, this one and this one. So the total pressure would just be the sum, 0.0758 atmospheres plus 0.846 atmosphere. So 846 plus 0.0758, rounding it to 3 sig figs, 0.922 atmospheres. Okay. All right. That, by the way, is section 10.5, gas mixtures. And there you go. Okay. We only have one more section that I haven't covered, and that is 10.6, kinetic molecular theory of gases. So I'll cover that tomorrow, and then we'll be pretty wrapped up with chapter 10. So ask any questions tomorrow, bring any problems that you're having. We'll have time for it because the kinetic theory, I can cover that in a half hour. I can take an hour for it because it's a pretty broad subject. But if you have any questions tomorrow, bring them with you and we'll take care of those. And again, feel free to reach out to me today, and I will put this, I know I did this last problem pretty quickly because I was running out of time. So I'll post this morning, and have a great day.
Thank you.
Thank you.
Professor, I have a question.
Yes.
Because I didn't saw that you post the grades for my lab, and I wasn't sure if you got my lab report.
Here, let me do this. Let me stop the recording. Oh, why is that not doing that? There we go.